Welcome to this session. Now, as discussed in the last class, we will be starting the cylindrical polar coordinate system. These cylindrical coordinate systems are quite common in various engineering problems. For example, the transport through a pipe in a tubular reactor. There are tubular cross section equipment where the mass transfer or heat transfer can take place. Heat exchangers, mass exchangers like dialyzers and other things. So, the tubular geometry and cylindrical geometry are quite common in various engineering problems. So, now in the last few classes we have looked in detail what will be the how the governing equation take the form in rectangular coordinate system and their solution. Now, from this class onwards, we will be looking into the cylindrical polar coordinate system, and later on we will be moving over to the spherical polar coordinate system. So, first we will be talking about the cylindrical coordinate system. Cylindrical polar coordinate system. The typical operator that one will be looking into is 1 over r. So, we will be as we have discussed that we will be encountering with the Bessel equation in case of cylindrical coordinate system, and the typically 0th order Bessel equation will be in the form of 1 over r d dr r dr is equal to minus lambda square. So, this will be in a sense d dr of r dr plus lambda square r is equal to 0. So, this is a typical Bessel equation, and first we will be proving in this. So, we will start with that this is the 0th order Bessel equation, Bessel function, they are orthogonal to each other. In fact, that is true for, we will be later on we will be generalizing it that any order of Bessel functions, they are orthogonal to each other. So, in this class we will just prove at the very beginning that 0th order Bessel functions are orthogonal to each other with respect to weight function r. Like in the rectangular coordinate system, we have seen the eigenfunctions like sine functions and cosine functions are orthogonal to each other with respect to the weight function 1. Now, in case of cylindrical coordinate system, we will prove that Bessel functions are orthogonal to each other with respect to weight function r. So, let us say lambda m and lambda n are two eigenvalues which are distinct corresponding eigenfunctions. 0th order Bessel functions are the eigenfunctions to this equation, to this Bessel equation. So, therefore, the corresponding eigenfunctions are J0 lambda n r and J0 lambda m r. So, eigenfunctions to this problem are the J0 lambda r, and corresponding to lambda m and lambda n, the eigenvalues, the eigenfunctions are J0 lambda n r and J0 lambda m r. That means, this equation will be satisfied by the eigenfunction J0 lambda m r, and this equation will be satisfied also by the eigenfunction J0 lambda n r. So, therefore, we can write that d dr of r d J0 lambda n r dr plus lambda n square r J0 lambda n r is equal to 0, and we can also write that d dr of r d j 0 dr lambda m r plus lambda m square r j 0 lambda m r is equal to 0. So, we will write it as equation 1 and equation 2. So, what next we will do? We will be multiplying equation 1 with j 0 lambda m r and multiply and integrate over the domain of r, and then we will be multiplying equation 2 with respect to j 0 lambda n r and then integrate over domain of r and then subtract. That means, what I will be doing next is I will be multiplying equation 1 with j 0 lambda m r dr, then integrate from over the domain of r from 0 to 1 and then minus 0 to 1 equation 2 multiplied by j 0 lambda n r dr. If we do that, let us see what we get. It will be 0 to 1 j 0 lambda m r d dr r d j 0 dr lambda n r dr minus 0 to 1 j 0 lambda n r d dr of r d j 0 dr lambda m r, then plus lambda n square r j 0 lambda n r j 0 lambda m r dr 0 to 1 minus lambda m square 0 to 1 r j 0 lambda m r j 0 lambda n r dr is equal to 0. So, if you look into these two terms, the r j 0 lambda m r j 0 lambda n r dr will be common. So, there will be lambda n square minus lambda m square. So, we will be looking into we will be breaking into the two equations, left hand side and right hand side completely. J 0 lambda m r d dr r d j 0 dr lambda n r dr minus 0 to 1 j 0 lambda n r d dr r d j 0 lambda m r dr, and right hand side we write lambda m square minus lambda n square integral 0 to 1 r j 0 lambda m r j 0 lambda n r dr. Okay. Now, let us evaluate the left hand side completely, then we will be turning to the right hand side. So, let us evaluate left hand side. So, we write down the left hand side completely 0 to 1 j 0 lambda m r d dr of r d j 0 lambda n r dr minus 0 to 1 j 0 lambda n r d dr r d j 0 lambda m r dr dr. So, we integrate this by parts. So, first function j 0 lambda m r, first function integral of the second function. So, r d j 0 lambda n r dr 0 to 1 minus 0 to 1 differential of the first function. So, d dr of j 0 lambda m r integral of the second function. So, r d j 0 lambda n r dr dr minus first function integral of the second function. So, j 0 lambda n r r d j 0 lambda m r dr from 0 to 1 minus minus plus 0 to 1 first function, differential of the first function. So, d j 0 lambda n r dr r integral of the second function d j 0 lambda m r dr dr. So, if you look into this integral is r d j 0 lambda m r dr d j 0 lambda n r dr, and these will be equal and identical, but they will be having the opposite sign. So, these two will be cancelling out. Now, let us put the boundary condition j 0 lambda m. So, this is nothing but the bilinear concomitant term r at 1. So, d j 0 lambda n dr minus when r is equal to 0, this term equal to 0. So, this will be returning a value 0 minus j 0 lambda m, r is 1. So, this becomes d j 0 lambda m, this becomes lambda n, d j 0 lambda m dr, and at r equal to 0, this will be 0. Now, since lambda m and lambda n are the eigenvalues, and we know that the eigenvalues will be the roots of the transcendental equation j 0 lambda m is equal to 0. So, therefore, j 0 lambda m is equal to 0 and j 0 lambda n is equal to 0, because the eigenvalues are roots of this equation. So, these will be equal to 0, these will be equal to 0. So, therefore, the whole left hand side will be equal to 0. So, if we now write down the right hand side, it becomes lambda m square minus lambda n square integral 0 to 1 r j 0 lambda m r j 0 lambda n r is equal to d r dr is equal to 0. Now, lambda m and lambda n are two distinct eigenvalue. So, therefore, lambda m is not equal to lambda n. So, therefore, lambda m square minus lambda n square cannot be equal to 0. So, the option that is left behind is this integral will be equal to 0. So, this will be 0 to 1 j 0 lambda m r j 0 lambda n r r dr will be equal to 0. That proves that the Bessel functions are orthogonal to each other with respect to weight function r. Functions are orthogonal with respect to weight function r. So, we will be utilizing this property of the Bessel function in order to solve the partial differential equations in cylindrical polar coordinate system, and then we will be after this, once we prove that the Bessel functions are orthogonal, then we will be looking into the complete solution of PDEs in cylindrical coordinate system. So, let us first take a two dimensional problem. This is transient one dimensional heat conduction problem. So, it is basically two dimensional problem, one dimension in space, one dimension in time. So, the governing equation will take this form del u del t is equal to 1 over r del del r del u del r. Okay. So, at t is equal to 0, we have u is equal to u naught, at r is equal to 0, we have u is equal to finite, and at r is equal to 1, we have u is equal to 0. Now, these boundary conditions we need to discuss about this. So, at time t equal to 0, u is equal to u naught means the temperature is it is maintaining a uniform temperature at time t is equal to 0. The boundary condition at r is equal to 1, u is equal to 0 means the at the wall at if so this r and u coordinate system, let us consider they are non-dimensional. So, r is equal to 1 means at the r by r is equal to 1. So, therefore, at the edge of the tube or the pipe, we are maintaining a constant temperature. After doing the non-dimensionalization, we can make the boundary condition to be homogeneous. Suppose t is equal to t naught at r is equal to capital R. Now, if you define r star is equal to r by r, then r star is equal to 1, and we define theta or u as non-dimensional temperature like T minus T naught divided by T naught, then u will be equal to 0 at r is equal to capital 1. So, this means we are maintaining a constant temperature at the wall, and at r is equal to 0, u is finite, means we do not have any value, we cannot measure the experimental value of temperature at middle point of the tube, but we know that there will be existing a a temperature at the center point. So, we put u is equal to finite there. So, this is an example of physical boundary condition. So, these will be dictated by the physics of the problem. So, this is an example of physical boundary condition. So, once we do that, then we go ahead with the separation of variable type of solution. So, u is supposed to be a product of two function, one is completely with a function of r and another is entirely a function of time. So, if you do that, then we will be getting r dt is equal to t 1 over r del r, in fact it will be d dr of r dr. So, then we separate out the variables 1 over t dt is equal to 1 over r d dr of r dr. The left hand side is entirely a function of time, the right hand side is entirely a function of space, they are equal and they will be equal to some constant. Now, if you remember, in the case of rectangular coordinate system, the very first instance when we solved the first problem, we checked the constant whether it is 0, positive and negative, and then ultimately came to a conclusion that for a particular case this will be giving a non-trivial solution, other two cases will become a trivial solution. Similarly, in this case also we will be checking three values of this constant 0, positive and negative, and then we will be looking into the solution and looking for a non-trivial solution. So, case 1 will be, let us say this constant equal to 0. If that is the case, then d dr of r d dr will be equal to 0. So, this means r dr will be equal to constant C 1. So, dr is equal to C 1 by r. Then we have one more integration C 1 ln r plus C 2. Now, at r is equal to 1, u is equal to 0, that means at r is equal to 0, your capital R is equal to capital R is finite. So, it will be obeying the original problem or original boundary condition in the r direction, and r is equal to 1, your capital R is equal to 0. So, therefore, if you put r is equal to 1, then for r is equal to 0, r is finite, means ln 0 is not defined. So, therefore, the associated constant will be equal to 0. So, therefore, this imposition of this boundary condition means C 1 is equal to 0. So, therefore, r is equal to C 2 and r is equal to 1, capital R equal to 0. So, therefore, C 2 equal to 0. So, therefore, your capital R is equal to 0. So, therefore, if you have this constant to be a 0 constant value to be assumed a value 0, then you will be getting a trivial solution. So, we are landing with a trivial solution if this constant is 0. So, therefore, this constant cannot be 0, because we are not looking for a trivial solution, we are looking for a non-trivial solution. Now, let us check the next possibility. The next possibility is this constant is positive lambda square, is positive, and let us say this is lambda square. So, this becomes 1 over r d dr of r dr is equal to lambda square. So, we will be having d dr of r dr minus lambda square r is equal to 0. So, if you open up this, it becomes r d square r dr square plus dr minus lambda square r is equal to 0. Now, we substitute y is equal to lambda r and see what we get. If you substitute y is equal to lambda r, then the derivative dr will be nothing but dr dy dr. So, this becomes lambda dr dy, and similarly we can get d square r dr square in terms of y as ddr of dr. So, therefore, this becomes d dy dr is lambda dr dy multiplied by dy dr, and this will be lambda. So, it will be lambda square d square r dr square. So, then we substitute these values, this derivative in this equation in terms of y. If you really do that, we will be having r lambda square d square r dy square. This will be dy square plus lambda dr dy minus lambda square r is equal to 0. Okay. So, then we substitute r by y by lambda in this equation, and after substituting that, the neat form of the equation becomes y square d square r dy square plus y dr dy minus y square r is equal to 0. So, this equation is nothing but, if we can identify that it is a second kind Bessel function of order 0. Okay. So, this will be as we have discussed about the special ODEs or special ordinary differential equation that we have discussed earlier. We can identify that this equation is nothing but the 0th order of Bessel function of second kind. So, the solution is composed of I0 and the superposition of I0 and K0. So, if you now write the solution will be nothing but R of y is C1 I naught y plus C2 K naught y, and y is lambda r. So, therefore, r, which is a function of small r, is nothing but C1 I0 lambda r plus C2 K0 lambda r. And now, we can put the values boundary conditions of the original problem at r is equal to 0, capital R is finite, that means, if you remember the property of I naught, the property of I naught is I naught as a function of lambda, it will be ever positive. On the other hand, if you look into the property of k naught by lambda, it will be infinity at r is equal to 0. So, therefore, the associated constant C2 is equal to 0. So, C2 equal to 0. So, therefore, R is equal to C1 I0 lambda r, right. So, therefore, since K0 is infinite at small r equal to 0, but capital R should be finite there. So, that there will be a conflict of concept. So, therefore, the associated constant must vanish at that particular boundary. So, what is left is R is equal to C1 I0 r. Now, let us put the other boundary condition at r is equal to 1. We have capital R is equal to 0. So, this will be equal to 0 C1 I0 lambda. Now, in this equation, as we have seen, the property of I0 is that it will be ever positive. For every value of finite lambda, I0 will be assuming a positive value. So, therefore, it can never be equal to 0. So, therefore, in order to satisfy this equation, C1 has to be equal to 0. This is not equal to 0, therefore, this means C1 equal to 0. We have already seen that C2 equal to 0 and C1 is equal to 0. So, therefore, solution is R is equal to 0. So, therefore, this gives me a trivial solution. Therefore, the case that the constant is a positive constant is ruled out. So, constant is positive, that cannot happen, it is ruled out. So, therefore, what is left is that the constant has to be a negative constant. So, let us look into the look into that option. The constant is this, that is case number 3. The constant is negative constant and that will be equal to minus lambda square. So, if that is the case, we write down the governing equation of radial varying part is r d square r dr square plus dr plus lambda square r is equal to 0. Now, next again we will be doing y is equal to a transformation y is equal to lambda r. So, this gives you y square d square r dy square plus y dr dy plus y square r is equal to 0. This is the 0th order Bessel equation of first kind, order Bessel equation of first kind. So, the solution is composed of J0 and Y0, C1 J0 Y plus C2 Y0 Y. And in terms of R, this becomes C1 J0 lambda R plus C2 Y0 lambda R. Okay. So, I will stop here in this class. So, in the next class, I will be taking up this problem and moving forward, moving ahead, and I will be completing this solution by using the separation of variable. Thank you very much.